Two hydrogen atoms far apart have zero energy relative to one another. Draw an energy curve to represent the change in their energy as they approach one another and as their nuclei are forced closer together than the natural bond length. This is the level 1 question where you simply have to draw a textbook diagram, which is there. Don't forget you have to label your axes, so it's the change in potential energy versus the distance between the nuclei. And then you're going to say that it's a weird graph because they're far apart to start with virtually no energy. It dips down, gets to a minimum energy, and then spikes up. And this, the minimum energy, the distance at that point is the bond length. Okay, define an anion and a cation and describe how each one is formed. So your anion is negatively charged, your cation is positively charged. The anion is formed when an atom gains electrons, whilst the cation is formed when an atom loses electrons. Define electronegativity. This is straight out of your notes again. It is the tendency of an atom to attract a shared electron pair, or a bonding electron pair. In a bond, you can say that as well. In terms of electronegativity, explain why hydrogen fluoride is a polar covalently bonded molecule. Now, they ask you specifically in terms of electronegativity, so you need to tell me, get some marks, write down the electronegativity. So let's look at the electronegativity difference there, and that is equal to the electronegativity of fluorine is 4, of hydrogen is 2,1, so that lands up equaling 1,9. Therefore, it is polar. It is covalent, it is two nonmetals, and therefore covalent. If I just said to you, what is the type of bond formed between hydrogen fluoride, you could have said ionic, because 1.9 is a very high electronegativity difference. However, this question was phrased saying it is polar covalent. Tell me why. Use Lewis dot notation to represent the bonding of the following. So first we're going to go with ammonia. Ammonia is NH3, and ammonia is therefore all nonmetals, so it's going to be covalently bonded. Nitrogen is in group 5, so there are 5 electrons. Hydrogen in group 1, there are going to be 3 hydrogens, and I'll end up showing the bonding electrons over there and showing that nitrogen believes it has 8. So I've represented a covalent bond. Aluminium oxide, slightly different, is going to be a ionic bond because aluminium is a metal and oxygen is a non-metal. So I'm going to have my aluminiums, which have each got 3 valence electrons. We don't know what its thing is, or what its picture looks like yet, so let's draw it slowly. We don't want to. Oxygen has got 6. I transfer from the metal to the non-metal, and notice there's still 1 more electron that needs a home. So best I get another oxygen going, and I notice that there's still now a hole in that oxygen. So I do another aluminium with 3 electrons. I need another oxygen to accommodate those last 2 electrons. And notice how when I'm doing an ionic bond, I show the transfer of electrons. What does that leave me with? It leaves me with 2 Al3 pluses and 3 O. Each of these O's have gained, do that, 2 electrons. So I show the formation of the ions. The ionic was worth 4, the covalent was only worth 2. From this list of solids, choose one correct answer for each statement below. So I've got these 4 substances over here. Let's try and just take that out of the way. Particles are held by strong coulombic forces. Strong coulombic forces exist in ionic and metallic. So I need to look which of these is ionic or metallic. And sodium is a metal, so it is ionic or metallic. And copper chloride is ionic, so it is a metal and a non-metal. So either one of those would have been acceptable. The bond between the atoms is polar covalent. So I have to have a polar covalent. The bromine is non-polar because it's Br2. And the ammonia is between nitrogen and hydrogen, which is definitely polar, so that is going to be your correct answer. Can only conduct electricity in the molten or aqueous phase. That is true of any ionic substance, so it must be the copper chloride. Bonds between the atoms are non-polar covalent. We've just discussed that. That's going to be your bromine. A good conductor of electricity and heat, that is an identifying feature of a metal, so that must be sodium. Substance is composed of ions, that must be an ionic substance, so again that's your copper chloride. Has a sea of delocalized electrons around positive kernels, again that's a metal, so it's going to be your sodium. And the molecule has a linear shape. If it's a molecule, it has to be covalently bonded, and the only two are ammonia and bromine. Ammonia is pyramidal, and bromine is going to be Br, and that is linear. We've now got a Maxwell-Boltzmann distribution curve over here. You do need to know these, and it illustrates the relative distribution in energy, so it's the amount of energy in a given sample at a specific temperature. Read the axes, number of molecules with a certain amount of energy. So lots of molecules have got little energy, few molecules have got a big amount of energy. Use the kinetic particle model of matter to explain the significance of the shaded area under the curve. So this is activation energy, and that's how much energy. Kinetic particle is how much the particles are moving. And remember, we're just talking about energy here, so that is movement. And what we're going to say is that all of these shaded particles over here have got more energy. You could even say more kinetic energy. And then the necessary activation energy. So there's more energy than the necessary activation energy, and therefore they have enough energy to react. We now get a table of various bond energies, and you consider the equation that's been given to you below. They also give you the structure of this ethane stuff over here, because you don't know it yet. Later in the year you will, but you don't right now. The diagram alongside shows the structural formula of ethane. Now it says calculate the energy needed to break the bonds of the reactants. Well, we need to draw out the bonds of the reactants. Firstly, we've got the ethane, but we've also got some oxygen, which means we need to start by saying I'm going to break 1, 2, 3, 4, 5, 6 CH bonds. But there are also 2 of those. So it's 2 times 6. Then I'm going to need to break 1 CC bond. But there are 2 of those. And I'm going to have to break 1 O double bond O bond. So that's going to be 494. But there are 7 of those. And when I do all the multiplying over there and adding up, I land up with 9082 kilojoules that you need to break the bonds. Now let's try and make the bonds. So we first need to draw out the shapes of these particular molecules. So it's carbon dioxide and water. You definitely do need to be able to draw those molecules. So let's do a similar thing that we have just done now and see what we need to break. So in 1 carbon dioxide, I am going to need to break 2 C double bond O's, and there are 4 of them. I then need to, in 1 water, I am going to break 1, 2 OH's, and there are 6 of them. When I add that all up, I land up with 11,900 kilojoules. Then they ask me to, that's the energy released, in other words, when we make bonds. Calculate the delta H for this reaction. I have clearly released more energy than I have taken in. So therefore, this is definitely an exothermic reaction. And I am going to say, what did I start with? Versus what did I end with? And I land up with a negative 2012 kilojoules. So that's my delta H. Classify the reaction. I've already done that. It's an exothermic reaction. And now draw an energy profile. This is considered a level 1 question. You really need to get quite good at it for this reaction and include the following labels. So the first thing is it's an exothermic reaction. So I'm going to have a curve that has that shape. This is called course of reaction. It's not time. And this is again your potential energy. Then if I'm going to do the labels, the energy of the product, the energy of the reactants I'm going to start with. That's your energy of reactants, the starting energy. The energy of the products is at the end. That's the energy of the products. Delta H is the difference between the energy of the reactants and the energy of the products, delta H. Then they want the activation energy. This is really the activated complex over here. The activated energy is the energy required to start it. So that's actually the activation energy over there. So you needed to put in all of those labels.